Humans have always wondered how the world works, and the best way to find out has usually been trial and error. What we call classical physics began in the late 1500s when, legend has it, Galileo dropped two different objects off the Leaning Tower of Pisa to prove that all objects fall at the same rate regardless of weight. And for the next 200 years or so, the same no-nonsense, seeing is believing approach enabled physicists to develop other sensible ideas like Isaac Newton's laws of mechanics and James Clerk Maxwell's laws of electromagnetism. Classical physics helped explain all sorts of things, from the existence of radio waves to the motion of the planets. Anything scientists didn't know, they believed they could learn by following Galileo's tried and true methods of devising experiments, taking careful measurements, and comparing the results against the predictions of mathematical laws.
Just as I hypothesized.
We classical physicists were so certain of our ideas that we compiled an entire series of fundamental assumptions. A list of what we irrefutably knew about the material world.
Number 1.
The universe can be visualized as a giant machine. Complicated movement can be understood as the simple movements of the machines in the parts.
Number 2.
All motion has a cause. When you see an object moving, you can always figure out what caused it to move. Maxwell, I thought I told you this lab is not a playground. Sorry, Newton.
Number 3.
An object's state of motion is known at a given point. It can be determined at any other point in the object's future or past. It's simply a matter of examining the object's momentum. What direction it's traveling, what it bumps into, what gravity it encounters, and so on. Simple stuff, really. We call this concept determinism.
Number 4.
Light can be understood as a series of electromagnetic waves that travel through space at the speed of, well, light.
Number 5.
Energy in motion can be represented two ways. As energy carried by a particle. Ow, ow, ow! Oh, you stupid apples. Or energy carried by a wave. Not that kind of wave.
Number 6.
It's possible to accurately measure the properties such as temperature or velocity of any system. All it requires is the right instruments.
By the late 19th century, classical physicists believed all these statements to be absolutely and universally true.
That's our story, and we're sticking to it.
But all six would eventually be thrown into doubt by quantum theory. Wrong.
Huh? What's that?
It turns out that classical physics works really well for things that are big and slow, like cars or footballs, or classical physicists falling through space. Quantum physics, on the other hand, deals with an entirely different world. The objects are very small, molecules and atoms and such, and they are traveling very, very fast. In 1859, Maxwell started examining the motion of gas molecules inside enclosed containers at different temperatures. He quickly realized it would be virtually impossible to accurately measure the individual velocity of molecules, especially a quadrillion of them.
Forget this.
So he decided to turn to statistics and probability to make some generalizations about the molecules. In other words, he used his best judgment.
That's close enough.
And in so doing, was able to predict the probable range of velocities relative to an average velocity.
That's completely ridiculous.
Quantum theory often relies on probability and sometimes seems to defy common sense. And that's according to the scientists who study it. Are you kidding me? It doesn't seem to add up. Despite this, quantum theory is awfully useful for explaining many things. The periodic table of the elements, the operation of lasers, the stability of DNA, and the origin of the Big Bang. As the 1800s came to a close, the scientific study of things no one could see was the new hot thing. It was the pre-quantum era, and the race was on to uncover the mysteries of energy, light, and heat. Everyone knows that if you stick something into a furnace and heat it up, it will begin to glow red. It doesn't matter what you stick inside. Glass, coal, that ridiculous ceramic dog your aunt gave you for your birthday. When it reaches a given temperature, it will always glow the same color, progressing through each phase of the color spectrum as it heats up, going from red to yellow to white to blue to ultraviolet and beyond. If heat were only allowed to escape from one small hole, it should be possible to accurately measure color frequency and intensity. Classical physicists of the late 19th century, like Lord Rayleigh and James Jeans, spent a considerable amount of time studying this concept known as black body radiation.
Hey, Rayleigh, throw another particle in there.
Throwing! All right, Jeans, hit it!
Hitting.
Oh, that's hot!
Wow, that was intense. I'd say at least 1900 degrees Celsius.
Dump a lot of particles inside a black body, heat it up, and the box will eventually fill up, limiting its maximum intensity to a finite and safe number.
Jeans, how about we throw a few electromagnetic waves into the old black body?
Why not? There's no limit for those. Brilliant.
Switch over to electromagnetic waves, which have no mass and take up no space, and theoretically there is no limit to their intensity and radiation. The shorter the wavelength, the more room you have for additional waves. According to classical physics, you could keep cramming that box full of waves and always find room for more.
Turn up the heat.
Turn on the heat, and every one of those waves would start vibrating, driving the black body's color frequency well beyond the ultraviolet, and its radiation to infinity, resulting in...
Oh, hot, 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 hot.
But this was obviously not the case.
Hey, Jeans, shouldn't your eyes be melting right about now?
Why didn't heated materials behave the way classical physics said they should? Why doesn't our own fireplace emit so much radiation as to blind anyone who sat in front of it?
Ow, my eyes!
Physicist Max Planck did not come onto the scene intending to create a whole new branch of science. He liked classical physics. He was simply trying to figure out why black body equations didn't match black body reality. In an imaginative leap, Planck envisioned a collection of electric oscillators inside the walls of the black body that vibrated faster and faster as the temperature inside the furnace increased, emitting energy the entire time. The higher the frequency, the more energy the oscillators emitted, which once again, according to classical physics, dictated catastrophic results.
Nice space.
This is going to hurt in the morning. I am repeatedly confronted with reliable data that cannot be explained by any accepted theory.
Unable to make the numbers work any other way, Planck turned to Maxwell's energy distribution for particles. What if energy came not in an unbroken continuous wave, but in a series of discrete energy chunks? When he plugged it into his equation,
Energy equals a constant h times the frequency of the light.
it worked.
Oh, joy!
Oscillators did not emit energy in a continuous range. Instead, energy was emitted via discontinuous and indivisible units, which Planck called
Energy quanta!
For any given temperature, the quantum of energy is given by this formula, where F is the frequency and H is known as
Planck's constant! Max Planck!
the quantum was born, and Planck's so-called electric oscillators were actually primitive renditions of what would eventually become known as the atom.
It's me again, Isaac Newton. In the 1600s, I was convinced light was made up of particles which I called corpuscles. I really had to duke it out with a Dutch physicist named Christian Huygens, who insisted that light existed as waves.
Huygens versus Newton!
Waves! Particles! Waves! Particles!
And then later, I, J.C. Maxwell, resolved it with my electromagnetic wave theory, saying light exists solely as waves.
But as physicists dug deeper into the atom, experiments made it increasingly clear that tiny particles at the subatomic level behave differently than objects in the visible world. A new set of mechanical equations was needed to describe these quantum mechanics. In one experiment, physicist Philip Leonard was using lights of varying intensities to blast electrons off a sheet of metal. Atoms on the surface of the metal absorb small amounts of energy, causing some electrons to fly off. According to the classical wave theory, the brighter or more intense the light was, the stronger the light waves would be.
I've got the light on full power, but the energy of the ejected electrons is next to nothing.
But then, when Leonard tried using light with a higher frequency,
Holy flying electrons!
a young German fellow by the name of Albert Einstein came along to take a look.
The only explanation for this photoelectric effect is that light has particle-like properties. But relying on Planck's constant, I prefer to think of light as small bundles of energy, which I will call photons. It doesn't matter how bright the beams of light are, photons have more energy at higher frequencies, not higher intensities.
But Einstein didn't stop there. He went on to say that light actually possessed wave-like and particle-like properties.
Now hold it right there, Buster.
Yeah, we already said that energy had to exist as one or the other. How can light be both?
Not just light, monsieur, but matter as well. Pardon me.
The French prince and physicist Louis de Broglie generalized Einstein's principle, applying it to the entire physical world.
Electrons, protons, photons, tout le monde. Everything has a dual nature.
De Broglie also proposed that electrons themselves exhibited wave-like behavior. These pilot waves adjust their wavelengths periodically, just enough to fit the electron into a stable orbit of a fixed radii from the nucleus. Only objects of a very small mass, like electrons, have noticeable wavelengths, because Planck's constant, h, is such a very small number. For the record, the value of h, which Planck realized could never equal 0, turned out to be 0.0000000, 19 more zeros, 6626. Unquestionably small, but not 0. It took a reclusive mathematician named Paul Dirac to finally settle the particle-wave dispute. Crunching a ton of numbers and equations, Dirac proved mathematically the dual nature of light and matter. Since that time, the wave-particle duality has been free of paradox for anybody genius enough to follow the math.
Particles, waves, particles, waves!
Gentlemen, please. You're both right.
Paul Dirac said that all matter and energy exists as both particles and waves.
And that goes for electrons, too.
Niels Bohr's classic model of the atom was familiar to science students everywhere. Electrons spinning around the nucleus like a tiny little solar system. And young scientist Werner Heisenberg didn't like models at all. He didn't even believe atoms were things. He thought of them more like a secret code.
If an atom can't be seen, it's not a meaningful concept. Your atom is boring, Niels Bohr.
Then, in 1926, Austrian physicist Erwin Schrödinger came up with a new atomic model that consisted of standing wave patterns around a nucleus.
I have found an equation that can be applied to any physical system in which the mathematical form of the energy is known.
So when Max Born came along with even more mad math skills, no one quite knew what to expect.
The wave function itself encodes all the information about the particles that can be determined through observation.
Right. In other words, using Max Born's equations, Bohr's orbits were now replaced with dark smudges where electron orbits might be found.
These are all the places the electron could be at this exact moment.
Born had found a way to reconcile particles and waves by introducing the concept of probability.
This is not probability due to ignorance. This probability is all we can ever know about an atomic system.
That's insane! What do you mean by probability? You're wrong, and I can prove it! Imagine for a moment sticking a cat in a box with a radioactive nucleus, which has a 50% chance of triggering a mechanism that will drop a hammer, breaking a flask of poisonous fumes and killing the cat. According to your matrix calculations, Max Born, the unobserved nucleus is a superposition, meaning it exists partly as decayed and also partly as undecayed. That's like saying the cat in the box is both dead and alive, which cannot be true. Ah!
Silly boy. Until the box is opened, the cat is both dead and alive. It's your act of observation that collapses the two quantum states into a single one.
Say what?
Open up the box and look inside.
He's alive.
100% alive. 0% dead. Your observation confirmed it.
Observation has always played a key role in science. Galileo spent his whole career demonstrating proper testing of theories through observation and measurements. But from now on, at least in the world of quantum mechanics, the very act of observing would have a direct effect on the thing observed.
Look at it as a wave, and it behaves as a wave. Look at it as a particle, and it behaves as a particle. I am now a believer of this new probability theory. In fact, I'll be so bold as to say that the description of any atomic state before observation is undefined. It has only the potentiality of certain values with certain probabilities. And my uncertainty principle states that the more precisely the position of a particle is determined, the less precisely its momentum is known. So, it was no longer possible to say with any certainty that every cause had a clearly defined effect. But that was okay, because as time would tell, all sorts of things from transistor radios to atomic energy to space travel and microchips would prove that quantum physics actually worked, but that the only certainty in this quantum world was uncertainty itself.